Yeah, so we are talking about distributed data processing. So how many of you deal with data or big data like engineering, data in any manner, mine, analyze, etc. Alright, cool. So the most common questions that I get asked around data is like, when does my data become big data? Like, this must be a common sight that you've seen at the back of the trucks. So I hope you guys can see it at the back. Or, you know, like we show off data. My data is bigger than your data. So, well, it's a common thing. So let's start with how did we reach a point of it being a big data or data being so massive where we have to even talk about it. Like, I mean, it's just data. Why do we need to talk about it? So let's start with a small business. You have a point of sale system which is connected to, it worked by itself, yeah. It's connected to a small MySQL database. You are selling stuff. So the problem that we're trying to solve here is, let's say we have to identify the most profitable products in form of the least shelf life. So the product that stays for the least amount of time on the shelf before it is procured, like after it's procured and before it is sold. Fairly easy to solve in this setup. Like, you just have a small DB, you just connect to it and figure out your answers. You go big in your business. Now you have multiple point of sale systems in the same departmental store, still connected to the same database. We have problems of failover, recovery, etc., all standard problems. We go one step bigger. Now you attach it to an ERP solution where the inventory coming in, you tie it to that as well, because you realize that calculating profitability is not just computing the point of procurement versus point of sale. You also need to take into account taxations or what it meant to get that product on that shelf out there, because the standard answer that you would find from this is that the dairy products or the poultry products are the most profitable products, but apparently they are not, because they have the least shelf life. So there could be something more. Now imagine this problem over entire, like you now are at scale of a huge departmental store. You have headquarters located somewhere in the middle of nowhere and you have sales point everywhere. Now, if this information was still to be computed, would you be able to do it at the same pace by just connected to a MySQL database? Now, millions of transactions are happening every day, probably every second as well. There are multiple points of interaction of sales and purchase. You could be buying via Amazon, you could be buying over phone or email or whatever. Now, all of this has to be ingested and you need to crunch that. Now, absolutely not feasible in the standard ways. Now, this is how we land into problem that now what do we do about it? So, one clear distinction that we'll try to make here is type of workloads that we usually have when we're dealing with data problems. Well, one are operational and the other is analytical. So that's the standard OLTP model that we always used to have, and on the right is OLAP model. So most of the OLTP stuff is categorized as online. Now, by online I don't mean web online. Online means that you make a purchase, an entry is made, whatever logistical checks that you had to do around data, is it sanitized, is it forming enough logs, you don't want to sell items more than what you have, all that is tackled by the OLTP system. And the stuff that we were just talking about at the back, now analyzing and crunching, is my business making money, is my business not making money, which are the product that I should invest in or I should not invest in, is usually done sitting at a pile of data and is done later. So you can clearly call it offline access. So these are the typical workloads that I really like to split it out as. And as we go further, we'll be actually talking more about the offline systems and not the online systems, because I'm assuming that most of you have already mastered those things. Well, I assume. So when do we call our data to be big enough? Now, this is not my terminology. It's a standard terminology which is used in the data engineering textbooks as well now. And a lot of people who have pioneered the same came up with this information. So we define as 3 V's. One is volume. Now, at any point of time, you have a problem if you have 2 of these 3. Any one in isolation is easy to address and solve using traditional ways. But if you have any 2 of these, you usually would look beyond your traditional systems of what you have. We'll come back, we'll later have a look at what traditional systems look like and what challenges do they run into. Now let's talk about volume of data for a moment. Now Facebook produces 500 terabytes of data a day. Stats from Facebook, I'm not making them up. And with that much amount of data, you need to look into where the advertisements have to go. Now, it's not just these online businesses. Like every time you sit on a Boeing flight which goes from the West Coast to the East Coast or vice versa, one flight produces 240 terabytes of data. Like really, is that too much huge? This is just too huge a data to process. And that's not one flight. There are 18,800 flights going across West Coast and East Coast every day. And you can imagine the amount of data they're producing. So, and we've reached this point because we have this tendency of, having data, so we will save it. Like, might as well save it. We are producing it. So, yeah, on the right, we have velocity of data. Velocity of data is when your data is coming in at a pace where you really cannot process it at the standard tools that you used to. One of the biggest consumers of velocity of data is telecom industry. Now, every time you're making that voice call or a cellular call, what happens is that these telecom operators are processing your call drops, quality of voice, analyzing frequency, see where the drop is, where the quality is going bad. Users on the fly are going to get shuffled as well. Now, this is done also taken into account previous considerations of a zone. Someone didn't like my presentation? Right. So, you have, these are being analyzed at a rate of around 20 million calls per minute. Now, this no mean a small feat, like this is, you have to ingest a data which is beyond your traditional computation boundaries. It's also used in a lot of other companies as well, fraud. Every time you make a transaction, you get a call from HDFC Bank saying that, did you make this transaction? Well, someone is analyzing it, someone is processing it. At least you feel good about the fact that someone is taking care. Then there is a break-in, like someone tries to access your account, you get a notification from Google that someone's trying to log in with an IP address which doesn't really look like yours. Is it that really you, or do you want to change all your passwords? Prediction, rewards, credit, all of the financial industry largely works around these. Variety of data. Well, as we are going forward, we do not have any single source of data producers. There are logs, unstructured data, semi-structured data, structured data, audio, video. There's data coming in every format. As I said, we have this tendency, we are in an age where we want to produce data and we'll say that, okay, we'll bother about it later. We'll look, and this largely comes from one of the previous talks. I think someone named Mr. Lalit Dutt, right? And he was making a point about that there are unknowns which you do not know about. So, you save data for what you want to analyze, but what when you don't know what you want to analyze? Someone asked a question from the audience. Well, it should have been in my talk, but anyway, it has already been asked. So, when you have that, you rather save everything and later bother about, okay, this is what I need to pull out and this is what I need to look at. For that, the superset has to be really huge. So anyway, pick two of these three. If you have them, you really have a problem and you should attend the rest of this talk, and otherwise as well just stay. So why bother with data engineering? Like, why do we analyze data to begin with? Most of it is covered in the previous talk, but I'll still quickly go through it. I didn't have time to change the slides on the fly. There are three kind of workloads that you usually have in analytical processing. One of them is descriptive. Descriptive is when you are looking at traditional data, you want to see that how did I behave in the past 1 year, 5 years, 10 years, 20 years, or as long as your business has been around. And you want to generate behavioral data out of it. And you want to see that, okay, you make pretty graphs out of it at the end of it, nothing else. Then there's predictive analysis. Predictive analysis is using the descriptive data, you use the same patterns, and now you want to superimpose that and see that, okay, can I make a prediction on what is it going to look like? Like, can I make a guess that maybe this brand of toothpaste is going to sell more in this particular store and not the other one? So coming back to the original problem of a departmental store, now you are trying to analyze that maybe I don't even need to ship poultry in the times of, let's say, in September or October, because people don't buy it. So this can help you make good guesses, and at the end of the day, you can make more money out of it because you're taking the right decisions in your business. And then there's prescriptive. Prescriptive is absolutely guesswork. I don't know how people do that, but well, they do. So as we move from left to the right, what you have to make sure is that this is deterministic behavior and you're moving towards probabilistic mathematics there. Now that is like purely into the game of machine learning. I mean, of course there as well, but now you're really making guessworks based on a lot of big polynomials that you really won't be able to solve on a piece of paper. Just a quick walkthrough. Descriptive is mostly done on historical, deterministic data. It's of the manner of inferential. Well, or if the managers usually make just pretty graphs out of it. A friend of mine makes a lot of money just doing this. So, yeah. Predictive. Predictive is future. It's probabilistic in nature. It's based on descriptive, and you try to take that information and try to guess what's going to happen later. Prescriptive is, well, Google Assistant, all kind of things. Most common example that I could think of. So now let's try to solve that architecture as round one, as we have been doing mostly, so all along. Let's say these are the sources of information that are coming in. There's transaction happening, there are events happening, there's semi-structured data happening somewhere, and the sources of information are kind of like 1, 2, and 3. And we're now trying to save them in some storage. One of the storage choices. Now, if there's a talk, there has to be Mongo in a big data conversation. That's why I put it there. So, there's MySQL. You would say that, okay, might as well just put it to Elasticsearch cluster, and I search it. The other day, a friend of mine was asking me, like, what did traditional systems look like, the big data system? Like, everything that ended at Elasticsearch was big data. So, now you have Elasticsearch and Mongo, and you try to build a small query engine around it where you're able to map and relate the data in all different sources. Storage choice 2, you say that, okay, you know, I don't really care about all these different choices of data sources. One database is good enough, so I'll take my existing solution like MySQL or Postgres because they scale well up to say 6 terabytes of data. I've read that in documentation, it works well, I've seen it somewhere as well. So let's dump everything into that database and we'll later bother about it. Now, over here we're putting everything into that simple thing and we call it a sort of a data warehouse. Now, where does it start breaking apart? Oh, you don't have the latest version of the slide, but then that's okay. So I'll come back to the slide later. So challenges. What are the challenges that we face with the regular architecture that we have? Well, one is vertical scaling, obviously. Now you're pumping in more and more data. And now this is where you have to make an interesting point. If you do not categorize the sources of your data and put everything into the same bucket, what you are effectively doing is you're paying for something that you want to access at low latency, and while you're putting everything aside it, as the system is going to grow, your costs are going to grow as well. Like just a comparative study. Like for, let's say, a gigabyte of data, you pay around $10 on a hosted Mongo system. Now, if you were to put everything into that system, when it becomes 2 terabyte, your cost is linear. It's multiplied by that. Not all data is of the same nature. So you have to categorize selectively saying that, okay, this is something that I need now. This is something that I need later. This is something that I need more often than not. While the other stuff, well, it's okay if I can get it at like say every hour or every one day as well. Sometimes that works as well. Now, so vertical scaling of a particular single database installation is going to be a huge challenge. Archival, well, because not all data is going to be relevant at all points of time, so you want to store them in manners which is retrievable later, albeit a little slowly with a bit of effort, but that's okay. Garbage purging. While we are pulling in data from left, right, center, every corner that we can, most of it is not going to be relevant after we have reached a maturity of an analytical system where we say that, okay, these are the things that we really do not care about ever in the life cycle of my entire analytical processing. Now, this seems to be taking a lot of space, or maybe it is redundant because too many streams are sending in the same data. Let's start purging it. And has anyone ever tried doing a delete operation on a large MySQL table or an alter table? You guys can relate with this problem in that case. Complex joins. You have left joins, right joins, and outer left joins, outer right joins, other joins. And as you grow, you know, they get really complex to tackle in your relational sense. Well, relations are complex as well over a period of time, and your queries become more and more complex and long. Now coming back to the old slide, and the group by operations. Now, most of the traditional systems start failing at a group by operation. Now, if you aren't using your indexes well, you probably would be doing a full table scan operation. Imagine a full table scan operation across billions of rows, which probably spans across multiple disks as well, or maybe if you have done a partition or sharding, then across the shards as well. Each of your cluster and a shard is actually going to be bogged down with one single query. Now you have to join them on a single driver, and that driver goes out of memory as well. So a group by or a join operation is going to kill your existing system. So how do we solve these problems? But before we solve this problem, I would actually like to take a step back on anatomy of what a data warehouse system looks like, or the layers at which it operates at. So the lowest layer that I usually categorize it is a processing network and storage layer. This is the underlying hardware. Now, this is the hardware which you pick for, and you obviously, each layer works independently of the other layer. By the way, this is my own work, so if any one of you do not agree with this, please feel free to talk to me about it. I would like to improve this. So if you look at each layer is independent of what the underlying layer is about, or what the consumer layer is going to look like. Now, as you add more and more computation, you obviously need more and more servers. You obviously need more and more drives, because storage is going to increase as well. You want to make those switches and hubs and routers faster and faster as well for faster network, because data is going to move across nodes. So this is the lowest hardware layer. And this is the challenge where infrastructure and operations usually come around. And this is where you need cluster managers. Like if you have heard names like Yarn. Okay, now from this point onward, I'll start putting and throwing in some popular names of tools and technologies that exist out there, just so that you can map them to what exists and what can be associated where. So the next time you hear a new tool and saying that, okay, how does this fit? Like I've heard of Spark, where does Flink fit? You can associate with, okay, what layer is it supposed to operate in? And you can take a more conscious and educated guess on, okay, do I really need this technology, or does it solve my problem? Like what exactly is my problem? So is this my problem? Then I need to look at a cluster manager, something which can help me bring up or bring down nodes, disks, network, on demand, or whenever I need it, or whenever the system needs it. A layer above that is file systems. File systems, because now remember we are talking about distributed systems, not a one single system. What that means is that we need file systems which are aware of where is my data going to be saved. Now, is this going to be saved on node 1 or node 2 or node 3? Now, this distribution awareness is where a file system like HDFS or ZFS or NFS and those kind of systems will come into the picture. Now, the difference there would be that HDFS is mostly in user space, whereas, just tell me the password. Right now, compute is a problem. So, I'll remember to swipe my finger on that thing. Yeah. So, where was I? Yeah, HDFS. So, the level at which a file system operates might change, but effectively all of them will be the exact same problem. Now, we go one level above than that, storage format. Now, data has to be saved in a file system. Now, this is where you will make a conscious choice of what do I save it as, because you want data to be accessible faster. You want to compress the data, because at rest you would wanted that, okay, maybe I'll just inflate it back when I receive it. So compression, decompression, all tackled into it. Or you might also want to look, how many of you are aware of column storages? Okay, who doesn't know column storage and would like me to quickly cover that? Is there anybody? Please raise your hand. Okay, there are ample hands. All right. Now, so I'll just quickly cover this up. Let's say traditionally we save data in, okay, yeah, that one went off. So you save data as rows, like each data is a row with a schema. Now you have, let's say you're saving an information of inventory, you would have an item code, price, label, brand, etc. All of these would be saved in per row basis. Now, one effective store that you can also use is by inverting the storage. So what you can do is store in columns. So if one column is called item code, the entire storage is going to be around an ID and a val, ID and a val. So in a large system like this, a column storage makes more sense at times. Again, it's not a general rule of thumb because it depends on your requirement, But why it would make sense is because column storage allows you to be flexible on the schema, because in a row based system, if you had, like, let's say if you're saving this all in a traditional table of a MySQL and a new column was added later, you would have to run an alter table or add a new column to it in the new schema. And again, imagine running this on a MySQL table which has around terabytes of data. Your system will actually choke, it's going to lock it down, and you won't be able to perform any other operation around on it. Now, an alternate way would be, if we were using a column based storage where the storage has been inverted in form of that new column will now only have the new IDs and the val according to it, the older storage doesn't have to be altered. So if that quickly explains what column storage is, I'll be more than happy to answer your questions in detail, so please catch me outside or any one of my team members who are around here. Now, so there are multiple storage formats which exist in form of H file for a system like HBase or Parquet or Avro, and all these are storage formats that have been optimized for such larger workloads. Now, over and above this, now you need a distributed processing framework as well, because every time I'm supposed to ask a question that to the data system that tell me how many people were buying this product around Diwali or around Christmas or around New Year or around 15th of August, whenever. Now, this question would probably span across multiple nodes, and across the data could be stored in any one of these components down there. You need something which can massively parallelize this operation. You really don't have to carry this operation as one single operation. So this sort of goes back into roots of functional programming, and what you are basically trying to do is divide an operation into smaller units and spread it around, and an aggregation of that would give you the result. It's like saying if you have to multiply 48 by 62, and so what you do is 62 into 48 is, you know what 62 into 1 is, you know what 62 into 2 is, you know what, now once you have computed 62 times 2 times 62, you can double that up, that makes it 62 times 4. Now you can add these unless it becomes 48, and you can distribute it around, so you get a product faster. Egyptians used to do mathematics that way. Now this layer over here is where your standard stuff like Spark, MapReduce or Flink and all Samza and all these will fit. Now over and above that is a query engine. Now query engine is a layer which basically understands what the query is and how is it supposed to be distributed on my compute framework. So query engines exist in form of, like, these are very internal to they are very tightly coupled with the distributed processing framework as well, but like graph query engines are one example. Spark has its own query engine in form of I think it's called Tachyon, and there are others as well. Now over and above that, the highest layer of this is the query language. This is the manner in which you interact with your system. Now query language, one of the famous ones is SQL, that's a query language. SQL is another query language. GraphQL is another query language. So these are query languages, are basically declarative languages. Most of the time declarative, they will always not be declarative, it depends on the language. These languages are, as a standard, going to be used for your consumer tools and entire tool chain that you have around it. So your existing MySQL client is, if it speaks SQL and your query engine and the distributed processing framework uses the exact same thing, then you can technically use the same MySQL client to query your data. Like one such common example of a query engine is Thrift. Thrift is a common name in the Hadoop system if you have used. So next time you run into a problem of a new name, first is see where exactly is your problem, and then try to map the tool to, okay, does it fit the layer in which I am having that problem, and see if it solves your problem. Now this is basically where we set up warehouses, etc. Now I want to come to the challenges of what challenges do you face in warehouse system as well. This goes slightly into the concepts of data modeling, And do you guys understand snowflake schema, star schema, or should I cover that quickly? Raise your hand if you would like me to quickly talk about that. Okay, that's a decent amount of hands, so I'll quickly say. So data that usually comes in is heavily normalized, and what you get is, this is how we save data in relational tables, like there is, okay, so before we do that, actually I'd like to cover another point. In all data analytical systems, one distinction that we always have to make is something a fact or a dimension? Now, this is the underlying ground that everything has to work around. Dimension is something which is going to remain static, like an item. When I say static, as in they don't change by, they really do not come in as, like event is a fact that happens around something. Let's take an example of a car sale and manufacture process. Like a car is a dimension. A sale record is a fact around a dimension. So whatever you call as metrics or events are actually facts. Like Earth is flat. Is this a fact or a dimension? Well, Earth is a dimension, and Earth is flat or round is a fact. It has changed over time. Like facts can change, but dimensions will pretty much inherently, these are the entities or actors of your relational system. So if this is a dimension may depend on another dimension, like a car may belong to a brand, a car might have an engine or a gearbox or tires. Now, all of these are dimensions which are also connected to other dimensions. Like a tire is not going to change, like it's a dimension, like it's a Pirelli tire or a Bridgestone tire. And there are facts around it. Now, one single common fact would be at the center, let's say a sale happened. Now, if you were to make this query on a system like this, most of the time your query engine is actually going to be busy making these joins. Now remember, we said that joins are expensive. So this system is really not going to optimize it for you. So what you have to do instead is you convert snowflake schema. Why is it called snowflake? Is because it looks like a snowflake, because each of these have new tentacles which are connected to different dimensions. And you convert this into a star schema. So star schema is basically the primary point most of the times of where data warehouse systems start, and this is what you need as a bare minimum to start doing your analytical workloads. Now this is where you have a common fact, and dimensions have been merged. So like this dimension, if it was a car, then it would have all the attributes of tire, gearbox, etc. all flattened out into one single dimension. So it's not the true dimension, it's a transformed dimension. And the reason why this is done this way is because now you have to do lesser number of joins when you have to make a query. It leads to a very interesting problem though, which I'll cover very soon. But if you guys can see it, then just hold on to that problem. Another thing is deduplication. Like when data comes in, and mostly these are asynchronous systems which are sending data from different, let's talk about that other problem of retail mart itself, point of sale terminals. Now these point of sale terminals are remotely connected, internet may or may not be there, so they eventually sync with the original data warehouse. Now they may resync, like the application developer who has written that code on the other side, and if it's seeding that data into the warehouse, this periodical sync in case of a network failure can happen over and over again. Now there is no way to watermark your point where you say that, okay, I have synced till point X. Now you can do this on every single record of your transaction. So you would do it in some batches, like I'll send 10 records at a time. Now what happens if the network fails while those 10 are being sent? So you would invariably, regardless of no matter how good code you write, which is fault tolerant or has all historics and all kind of things inbuilt into it, you will run into a problem where there will be some duplicates which are sent. These duplicates have to be handled at an ingestion time of the warehouse system. One of the standard ways to do this is something called Bloom filters and cuckoo filters, which is an alternate implementation of Bloom filters. Now, how basically they work is that given a stream of data which is coming in, you keep an array of what has been. So one interesting property of these filters is that they can never tell you whether something exists or not, but they can certainly tell you that this is something not present inside it. So the nature of the question that you ask to the filter sort of changes. So you can never ask that, have you seen this value earlier? Bloom filter can only tell you with a probability that I may or may not have seen this. But have you never seen this value? They can tell you with a certainty that yes, I have never seen this value. So in a sample implementation like this, like these are the objects that is already seen. Inside it does a multi-hashing and saves it across a fixed storage space where the index locations can actually be duplicated. And when you get a new object, you see that, have you not seen this? And if the Bloom filter says that, yes, I have not seen this, only then you actually go forward and ingest it into the warehouse. So this very effectively handles your deduplications. But one thing to understand is that duplication most of these things can only be done across a window of time. Like you cannot say that deduplicate over an entire year, because if your entire year had 2 terabytes of data, a new event comes in, you can't search over the entire terabytes or petabytes of data. So you'll have to do it in a finite window that you define. Let's say, find me duplicates in past to a fortnight or a week or 10 days. I mean, that's a call that you have to take on how your system is implemented. Now, if you come back to the star schema, where we said that, in a snowflake, dimensions are actually merged into a common dimension while ingesting into the DB. Now, there is a probability that a dimension has changed over time. Now, this is one of the most common and the most challenging problem that a warehouse system can face. Primarily because you dump data today, you do analysis day after tomorrow. Now, when you look back at that data and you want to do an analysis and you do the cross joins across tables, and if these tables are only carrying today's value, you can never do a point in time check. So if I have to find, let's say, certain goods, let's take that same example again. I'm trying to find the most profitable goods which have the most profitable shelf life. Now this shelf life is dependent on a lot of things, on transportation of the goods as well. Transportation is dependent on oil prices. Oil prices change almost every day. Well, not until recently they were fixed, but they change. Like globally they change every day. So when you want to do that analysis, you want historical data that for that particular fact, I want to do a join on the dimension value that existed back then. So what you are trying to track is a dimensions journey through time as well. That dimension value looked like this back then. Like let's take an example of the car thing itself. Like a tire used to cost 10 rupees back then, but today if it costs 1000 rupees or 10,000 rupees, when you do an analysis today of 10 years of data, you only want to look at that 10 rupees, not 10,000 rupees as it exists today. So the way to implement this problem is called slow changing dimensions, or acronymed as SCD. There are multiple ways to solve this. One is, as always, you ignore it and you do not solve it. So like you only get today's data. No, I mean it's actually a theoretically, like in science they call it type 0, which is ignoring the entire thing, that it doesn't change. Then there are type 1s where you say that I can override the values or not change the value at all. I'll keep it as it is and I'll never change it. Or you can add certain time filters next to it where you say that start time of this value was this and end time was this, and next time when you're making a join, you can see when the fact had arrived and do a join on anything which is less than end time and greater than start time of the value. This is fairly explained very well across the Wikipedia article as well. Usually I find Wikipedia too overwhelming and not explaining at all, but for this rare exception, they have done a good job. So just spend, maybe you can just look this up. They'll really thoroughly explain you what the solutions are as well. Batching versus streaming. Now this is one of the most common questions that I get asked, and probably because, as I promised, this talk is about buzzword, so I had to add this in. Now, batch versus stream. These are two inherent different kinds of problem and different kind of data sets. Now, what you can do against the streaming data is one What's that buzzer for? Oh, am I over time? Oh, okay. Okay. Are all projectors down or can you guys see over there? You guys can? Okay, so should I continue? But what about the guys in the front? Or you don't care? Oh. Okay. So back to batching versus streaming. Like one of the most important questions that I am asked, and probably you will face as well when you try to go about starting on your big data projects or trying to implement what tool and what framework is good. Now, inherently there are two different kind of problems, both streaming and batching. Batching is done on huge loads of data and always done usually in retrospect. You can use batch analysis to emit something like cuboids of data. I'm going to cover that very soon, or pre-computations which are next going to assist your streaming. Like now to put this into perspective, let's say a real-time transaction is happening in your banking system. You want to check whether this is fraud or not. What are the easy ways to check fraud? Like one easy way is by looking at all historical data, you can take quick patterns on that, hey, when transactions happen after 11 p.m. from this IP address, they can be fraudulent. Now you can use this as retrospective analysis, feed this as a quick filter to your stream which is coming in and do a quick analysis. So these are two absolutely disconnected processing events, and but still the question asked on one versus the other. And so we must be able to separate out that while we are doing streaming, you cannot go check the entire earth for is this a valid transaction or not. Well, you can if there is no one waiting of the transaction on the other side. But for an IoT device or a real-time system where events are happening, like for, let's take a flight tracker. This happened in Nice as well when the bus incident happened. Now, when one of the unfortunate event when bus had rammed into a bunch of pedestrians, the alarm that went off was actually 3 hours later, and people thought that was a separate attack altogether. So this is where you have to understand that streaming has to happen faster. All analysis have to happen faster in a way where you might take assistance from any of the other analysis that you have preceded by doing any batch analysis earlier. Out of order processing. Now, if you have a asynchronous system where you are sending events, it is quite tough to sort of guarantee the order in which it arrives. Like one event might arrive after the first one, where it was supposed to be in order of T1, T2, T3, it might arrive as T2, T3 and T1. Now imagine if you are generating reports and you are computing these nice pretty graphs where you're doing some analysis and probably some thresholds as well, actionable alerts on that. And after all that is done, an hour later, an event which was supposed to be done for an hour back arrives. You will have to go through that entire chain of pipelining again, like transform, deduplicate, recompute the entire thing. So out of order processing is something which is very crucial to your warehouse, and there are n number of ways to solve this, but as a challenge, it's worth putting this out on the table because there's no like X way that do this and this will solve your problem. But one thing that you can apply here is by taking a window of arrival, by deferring your compute slightly and say that I'm going to only process after 5 minutes of buffer. This is sort of where buffers and disk buffers, etc. will also start coming into the picture, that I'm going to stack these up for a window of 5 minutes, and every 5 minutes I'll do an analysis of what comes in what order, and whatever might arrive after this, I'm not going to process this at all. Like that could be one very quick way of solving this. While we're talking about data warehouses, data cubes are a very important aspect of it, because data cubes and data marts as well, I would very quickly cover that as well. Data mart is actually nothing but just a siloed view of a warehouse which is given to teams as only read-only access. Well, warehouse is mostly read-only, but this is a further narrowed down version of, let's say your entire warehouse consists of inventory, sales, salaries, profit, loss, whatever, everything is inside that systems. To the to the HR department, you would rather only expose the salary view, which is one data mart for them. You might have another view, which is a very siloed view of, let's say, inventory management to the procurement team, which silo will be called data mart. Cubes are just a view of your data, which could be multi-dimensional as well. Why cubes are done in first place is for efficiency of retrieval, because warehouses, as they are massive, they also suffer the same problem that you cannot ask a query quickly. Like, it has a certain threshold. You can optimize that, but that's going to take you a lot of cost to have a single digit millisecond warehouse. It's almost next to impossible. But if you want something like that, you want to build a real-time analytics graph out of it or a stream out of it, you will have to build cubes. Cubes are pre-computed. They could be computed on demand as well. In terms of SQL databases, think of them as either views or materialized views. And these are snapshots that you create, which get pre-computed and pre-populated. Now let's take a sample example of item location, day and quantity. This table, if you are familiar, can serve a lot of queries, like on this day, how many items were sold for this location? Or how many times is this item sold on that day? So it's sort of a multi-dimensional query view for you. Effectively, it's just a table of SQL. But if you have to visualize it, you can visualize it as like this. Like, if this was day axis, this is the location axis, this is the item axis, then each point here is actually the quantity which is being sold. So you can actually get faster results using this. Standard operation that we use on this is called slice, dice, and rotate. If you revisit the architecture very quickly, this is one sample implementation that we had done. So you have an event queue coming in. There are workers. These workers are responsible for sanitization of data, star schema conversion, deduplication, out of order processing, ensuring they are in orders. You take that data, you very quickly save that into a cheap storage, which is done for effective archival, which could be something like a blob storage of S3, which can be mounted as a SDFS system. Basically, this acts as a file system. Now, try to map this to the same anatomy. This is the file system layer. Next is you want a compute framework which can actually access this, do your queries, analysis, etc. You can use something like Spark here, or Apache Flink, or well, you could use a hosted EMR, and you'll find tons of other solutions out there as well. Now, this is where the compute framework will do its job, generate transformations for you, create temp tables, and finally output it into a cube system. One such cube system which is very popular for data analysis called Druid, Apache Druid. You can use that as well. And Druid has now this capability of serving very fast cube views for analysis purposes. And if one aspect of the consumption of warehouse was data visualization, you can use a tool like Tableau to analyze your data. That would be it for my talk, if I'm well in time. And
we'll take about 2 questions. And if anybody has any more, please reach out to Piyush. We are going to have a coffee break in some time anyway. Questions, anyone?
I see a question there.
Hi, Piyush.
Hello.
Just a quick question. Do you have any observation based upon the kind of projects you're doing, points of distinction between Spark streaming and Flink?
So,
any hands-on information?
Yes. I'll probably take one step back to address your question, and I hope I'll be able to answer it. And that is, so how streaming effectively is underneath window operation. Like, you can't apply something on an infinite stream. You have to do a, is that me? Or anyway. So, yeah, so stream is actually a window operation. So you define a small window and you say that I'll take, now this window could be bound by 2 things, either size of the window or time of the window as well. And you say that, you know, for these 5 minutes, 5 minutes is actually too long a time. For streaming, you probably would bring it down to 5 seconds or sometimes 500 milliseconds as well, depending on the rate of ingestion. And this window operation is what will define what is going to be processed as a batch. Now, Spark streaming underneath is micro batching. So they use the exact same batching code that they wrote for earlier when there used to be a batch processing system. They have taken that to Spark streaming. Now, whereas Flink is actually streaming first. They don't reuse the same code. So what that means is that Spark streaming has a problem of, I'm actually answering this question before the newest release. So the newest release doesn't have this problem. They've revamped a lot of code. Had a problem of back pressure. Because if your stream is not processing fast enough, you are actually going to fall behind and you're going to have stream overflow. So Spark streaming used to have that problem, whereas Flink was done as streaming first. So on Flink, it's the other way around. Batch is stream first. So you basically pick up a stream and then you batch it for an operation of yours. So that is probably the difference that you're looking for at the crux of it. Of course, there's an API difference, like you can do transformations on stream faster in Flink. Any other questions? Okay, thank you.
Thank you.